Hey, good morning. Today we're looking at section 4.2. We're looking at differentials. There we go. And what is a differential? We're going to look at that dy and dx a little bit separately now. We're going to see how does y change with respect to the change in x, and that's where the differentials come in, and we can separate the dy over dx. So this whole time when I've been saying notation matters, notation matters, notation matters, this is a case where we want to use dy over dx instead of y prime. So what's a differential? Let y equals f of x be a differentiable function, and let delta x denote a change in x. The differential of x is denoted as dx, sometimes delta x, and the differential of y is denoted as dy. And so what we have is dy is equal to f prime of x dx. Well, they kind of jumped over where that came from. We know that dy over dx is the same thing as f prime of x, right? So now we can multiply dx to the right-hand side. So dy is equal to f prime of x dx. And sometimes you'll see this written with the deltas. Delta y equals f prime of x times delta x. Okay, what does that mean for us? Well, let's start with the equation of a tangent line. We've done lots and lots and lots of that already. I know that y equals x e to the x. For the equation of a line, y minus y1 equals m times x minus x1. You know that's what we have to fill in. We already have the x and y of 0, 0. So what's missing for us? The slope. Let's find the derivative. dy over dx is equal to the first times the derivative of the second plus the second times the derivative of the first. I'm going to factor out an e to the x because they both have one. And now we're going to evaluate this when x is equal to 0. So dy over dx when x is equal to 0 is e to the 0. 0 plus 1, e to the 0 is 1, 0 plus 1 is 1, so this is 1. This is my slope. Some of us have been putting an expression with an x in it for the slope when I have the equation of a line. That's not correct. And that's my fault when I keep saying derivative is slope. The slope at a point. So you want to make sure that you're using the x value in there. I don't want to see expressions with e to the x or x in here for the m. And this is x minus 0. So y equals x is the equation of the tangent line at 0, 0. All right, no big deal there. But what does that have to do with differentials? Well, the idea is this. Let me scroll down a little bit. Maybe, there we go. If I have the equation of the line, and this pink line is y equals x, that's what we just found up above, and I look at x times e to the x, that's the blue curve that's on this picture, this blue curve. What happens progressively through A, B, and C is we zoom in closer and closer and closer to the origin. And if you zoom in far enough, look how close this is. We're into the hundredths. That curve starts to look like a straight line. And that's what happens with all of these. If you zoom in close enough, any curve can be approximated by a straight line. And that takes us to the linear approximation. So the closer delta x is to 0, the closer dy is to delta y. So we conclude that the closer delta x is to 0, the less the tangent line departs from the graph of the function, meaning it's a better estimate. So we pretend it's a linear approximation. This is the equation for a linear approximation, but I don't want you to be afraid of it. It's really just the equation of a line. L of x, f of x sub 0, that's the function at a point, so that's your y1. F prime of x sub 0, that's your m, and x minus x1. And where did that come from? It came from point slope. So earlier in the year when I said, hey, sometimes you'll see this where we just add the y1 to the right-hand side, that's why, because I knew it was coming up here. So yes, this is your linear approximation formula, and yes, this is how you'd see it with function notation, but just keep in mind it's coming from point slope, and we're just moving that y1 over to the right-hand side. That's all we're doing. An overestimate versus an underestimate. When the tangent line is above the function, the linear approximation is an overestimate. When the tangent line is below the function, it's an underestimate. So on this first picture here, My tangent line is an underestimate. Here it's an overestimate. This one's one of each. So to the left, it would be one thing, and then to the right, it would be another. So just be careful with those. This is jumping ahead a little bit, but that's okay. If my original function, we'll say this blue one is concave up, then my tangent line is an underestimate. In the second picture, we would say this is concave down. And then my tangent line is an overestimate because it's above. And again, these two, this one switches from concave down to concave up to concave down. So it switches whether it's an over or underestimate. Example 2, find the linear approximation for f of x equals sine of x near x equals 0. Then use L of x to approximate those 1, 2, 3, 4, 5 values. All right, we want to see how close and how far they are. So we need L of x is going to be f prime of x sub 0. That's kind of like your C, your starting point, plus f prime of x sub 0. That's your slope, times x minus x sub 0. All right, so near 0, my x sub 0 is equal to 0. That's where we're centering all of this. So we need to find a derivative. F of x is equal to the sine of x. F prime of x is cosine of x. No problem, we know that from our golden ticket. Now we're evaluating this at 0, so f prime of 0 is equal to cosine of 0. Cosine of 0 is 1. Keep working on those unit circle values. You have to have those memorized. So when I replace things, L of x is equal to, we have to come back to that because I didn't find that. The slope is 1, x minus 0. Now my f prime, nope, this one shouldn't have a prime. Got a little prime happy there. F of x sub 0, that's really the y value at your initial point. So f of 0 is the sine of 0, and the sine of 0 is 0. So this is a 0. This is a pretty boring line, but L of x is equal to 1x. Now, if I want to evaluate it at these values, first thing to know is you are in radians, not degrees, but you would put each of those values, excuse me, in place of this x. So let me switch colors here. L of negative 0.3 would be 1 times negative 0.3, negative 0.3. L of 0.1 would be just 0.1 because we're replacing it with the x. L of 0.4 is 0.4. L of 0.5 is 0.5. And L of pi over 4 would just be pi over 4. Now, you just want to remind yourself that these are approximations. So what do I mean by that? Well, if we actually calculated, and here's a good one, pi over 4, I'm going to come over here to the left. My linear approximation, that's why we use L, of pi over 4, we said is pi over 4. However, remember we're approximating the actual curve. So what is f of pi over 4? Well, f of pi over 4 is equal to the sine of pi over 4, and sine of pi over 4 is root 2 over 2. So pi over 4 and root 2 over 2 aren't the same thing, but you would find those decimal equivalents. I have my calculator here. Pi over 4 is 7.785. And root 2 over 2 is 0.707. So the values are close, but they don't match exactly. That's why we say that it's an approximation. The differential can be used to approximate change. So these are word problems, but don't panic. They're the easiest word problems that we'll do all year. We have a spherical bearing, has a radius of 3 centimeters when it is new. Use differentials to approximate the volume of the metal lost after the bearing wears down to a radius of 2.0 2.971 centimeters. Find the actual volume lost and compare the approximation to the actual volume. So let's talk about our differentials. We're talking about volume of a sphere. So volume is 4/3 pi r cubed. We want to find the derivative. This will be dv dr is equal to 4/3 pi 3r squared. Now we can multiply the dr to the other side. So dv is 4/3 pi times 3r squared dr. What's going to cancel out here? Well, the 3's. So the question is, estimate or figure out how much volume is lost. That's going to be our dv after we wear the radius down to 2.71. So how do we put these values in? The change in the volume is going to be 4 times pi. R is the original radius, so that's 3. dr is how much has the radius changed. So dr is really 3 minus 2.971. That's going to be a pretty small decimal, right? 7129, 0.029. Let me double check my math. I don't want to tell you something that's incorrect. Okay, we are. I had to look in the other spot. And because we lose that, we're going to go with the negative value. So the change in the volume is negative 3.2280. Now we're talking about volume, so it should be centimeters cubed. And I should probably not use an equal sign. I should use this little curvy equal sign that means approximately. So the second piece is to find the actual volume lost. So this is where we go back to geometry. So your volume lost, the original volume would be 4/3 pi r cubed, which would be 4/3 times pi. The original radius is 3 cubed. So in my calculator, I'll do that differently. That's okay. 3 to the third times 4/3 times pi. So this is 113.079. And then you could find out with the later radius, the second radius, 4/3 pi times 2.971 cubed. I'm just going to put this right in my calculator. 2.71 to the third times 4/3 times pi. And this gives me 109.849. And if we subtract those two things, my actual loss is negative 3.229. It rounds a little bit differently. But you could say, hey, our estimate was pretty good. So when you're talking about really small differences, you can assume that it's a straight line, or you can approximate it with a straight line, would be a better way to say that. Example 4, the diameter of a ball is 10 centimeters with a maximum error of 0.2 centimeters. Estimate the maximum error in the surface area and volume. So error is that change, again, that delta. We're going for delta surface area and delta volume. So let's do surface area first. So the surface area of a sphere is 4 pi r squared. Yeah, you should probably know what those are, but we'll keep working on those. So the change in the surface area with respect to the radius is 4 pi. That's just the coefficient in the front. The derivative of r squared is 2r. We'll multiply both sides by dr. 2 times r dr. Sorry, my handwriting is kind of yucky here. 4 pi 2, so what's the radius? Well, if the diameter is 10, your radius is 5. The change in the radius, we'll have to have that as well, would be 0.1. So we want 0.1, and we want 5. So 10 times 0.1, so this is 4 pi. And what units are we talking about? Centimeters squared. So that's the approximate error in the surface area. If we do this again, this time with volume is 4/3 pi r cubed. The change in the volume with respect to the radius is dv dr. So about 4/3 pi 3r squared. I'm going to multiply both sides by that dr. I know it feels weird at first when you do it because I said you can't separate those things, but we can. Here's 4, here's pi. My radius is 5 squared. My dr is 0.1. So what do we have? 25 times 4 is 100 times 0.1 is 10. So the error in my volume is 10 pi centimeters cubed. All right. Number 5. A box is to be constructed in the form of a cube to hold 1,000 cubic feet. Use a differential to estimate how accurately the inner edge must be made so that the volume will be correct within 3 cubic feet. So this is my dV. So cube. So your volume formula for a cube is side squared, side cubed, because all the sides are the same. We want to find the derivative. This is dV, ds. You can use an x or another variable as well. 3 side squared. I'm going to multiply the ds to the other side, 3 side squared ds. Now, a box is to be constructed to hold 1,000 cubic feet. So if my volume is 1,000 cubic feet, side cubed is 1,000 cubic feet, the length of a side is 10. So dV is 3 times 10 squared. ds, well, remember up here, we have to have the volume correct within 3 cubic feet. So that actually goes on the left in this problem. So ds, when we do a little canceling here, will be 1 over 100. The change in that, or the error in the side length of the cube has to be 0.01, and that would be measured in centimeters. Okay. Now, this is a topic, it's something that you should see in calculus, but it's not tested on the AP exam. So I'm going to put it right here. Not on AP. But it is included in a typical Calculus 1 course. So when you go off to school next year at college or whenever you're headed there, I just want to know that I've shown it to you. So Newton's method is a way that we can approximate a value by using this formula. So C is any given x value. And if you want to find the 0 where it crosses the x-axis, this is where we use Newton's method. So here's a function, whatever it looks like. I know that it crosses between 0 and 1. Well, I could use the 1 or the 0 up here in Newton's method to try to get myself closer and closer and closer to this x-intercept. So it uses the given y value, it uses the slope from there, it finds the y value, it uses the slope, it uses the y value. So it zigzags back and forth until it centers on the actual 0. It works for things that don't factor, but for us, it doesn't make a lot of sense because we have these. And with these calculators, you can go through and you can find the actual 0. I know that you know how to do that. If you only had a scientific calculator, the ones without the graphing features, then this Newton's method idea would be much, much more useful. So I think I have one example. Yep, that's it. So let me show you this. Use Newton's method to find the 4th approximation to the positive real 0 of that following function. So what does that mean? It means my first approximation is going to be, here's the thing, they didn't give us a starting value, did they? All right, so here's what I'm going to do. I'm going to graph this. X cubed plus x squared minus x minus 2. Okay, so here's my picture. It looks like it's crossing the x-axis pretty close to 1. So that's what I'm going to use for my starting value. I'm going to say that c sub 0 is 1. So 1 minus. Now, this is where a table might be helpful. If I have my original function in y1, I can take the derivative. Let's squeeze that in here. The derivative is 3x squared plus 2x minus 1. Do a little bit of rearranging here. I'm going to put that to y2. 3x squared. Okay, so I have them into y1 and y2. Now the thing that happens is if you go into your table, you have the values calculated for you already, which is pretty awesome. But I need mine to start at 1. Oops, it just graphed them. Okay. There we go. So when I go to use Newton's method, I want the function evaluated at 1. So that's my blue column of a -1 over the derivative evaluated at 1. And that is 4. So when I put this all together, 1 minus a -1/4, I have 1.25. Great. So I'm saying that it crosses the x-axis. Let me go back to my graph at 1.25. And I know it's teeny tiny, but you can see that blue curve. Okay, sure, it crosses at 1.25. So we do the second approximation. This is 1.25 over, well, now I want to try it all again. So in my table, you can do an ask, but I'll just do table set. Instead of auto in my independent variable, I want it to ask me. That'll be even quicker. So now if I go to my table, all right, they want me to put in 1.25, that's my last value. So y1 is 0.26563. 0.22563. And then the derivative, that's my red column, is 6.101075. All right, so I'm going to go back to my original screen. I'm going to do a little calculating here. I'm sorry I can't pull up the calculator on my laptop to share here. It's really unstable and keeps crashing, so I got to figure that out. Here's what it looks like in my calculator. So I have 1.206. Do I expect it to be close to the previous one? Yeah, I do. It's no surprise. And I know that this says to do the fourth approximation. Let's stop at 3 because I think you get the right idea. So this is 1.206 minus, I'm going to go back to my table. It's still in the ask, so I'll put in 1.206 by 0.00249. And then in the bottom, I have 5.7753. And while this particular skill we don't need in our in our course, there's something we'll do later called Euler's method, where we have to do this kind of repetitive process where we put numbers in over and over and over again. So it's good setup for that. I have 1.205. Now, if you keep going, obviously these values will get closer and closer together. And so when they start to repeat out here in the later decimals, that's when you know you found the true zero, when it crosses the x-axis. So great job. Rewatch whatever you need to. And I'll see you soon.